Stu Whittington, but he couldn't be here. So we have a video, which hopefully I can find. Yeah. Oh, I should do it. Yeah, I should do a video. Yeah, sorry. And so on. Okay. Full screen.
I'd like to start by saying something about my initial connections with Richard. So I first met Richard when he was a graduate student, I guess, at King's College in London, working with Jeff Joyce and David Gaunt. We really get to know one another in about 1990 when I was in Melbourne visiting Tony Gutman. And the three of us worked on a problem then about a phase transition, a collapse transition in partially directed walks. It was a nice problem to do because I think all three of us made a contribution. That paper wouldn't have been written without all three of us chipping in our oar for it. Then Richard and I worked again together in the middle of around 2005, again when I was visiting Melbourne. And we were working on a problem associated with directed paths, things like Motzkin paths and Dick paths confined between two parallel lines as a model of steric stabilization and stability of colloids more generally. So what I'm going to talk about today is vaguely connected to both of those, although it's a self-avoiding warp problem, not a directed warp problem. So let me see if I can make this work. So the problem that I want to talk about is going to be a self-avoiding walk interacting with a surface, but where there's a force which can pull the walk off the surface. So it's a mixture of an attractive force coming in, pulling it into the surface, and a force trying to move it away from the surface. And this is a connection to a real physical problem, which is polymer absorption. So if I have a linear polymer molecule in solution, in a dilute solution, then it can adsorb at a surface. And for me, at the moment, the surface is going to be impenetrable. And if the polymer is infinite, there'll be a phase transition. That is, there'll be a singularity in the free energy as the temperature changes. And at low temperatures, it will be in an adsorbed phase where a lot of the polymer is in the surface. And at high temperatures, it will be in a desorbed phase. So there's a characteristic temperature at which the phase transition occurs. Now, if the polymer is adsorbed, it can be pulled off the surface if we apply a force. And the way in which you're going to apply a force is by atomic force microscopy. That's the picture I want you to have in mind. So here's a sketch of what atomic force microscopy looks like. So the red dots correspond, first of all, the horizontal black line corresponds to the surface. The red dots correspond to monomers of the polymer which are sitting in the surface. The squiggly black line is the polymer, and this yellow or green triangular object is the tip of the atomic force microscope, which is coming down. It's grabbing the polymer somewhere, and mainly for simplicity, today it's always going to grab the polymer at the end, at the last monomer. And now if the AFM tip is retracted, that is, it goes upwards, it will tend to pull the polymer off the surface. So that's the physical background. And in order to look at this, we need to build a model. And the model that we're going to look at is self-avoiding walks. So you need to know a few things about self-avoiding walks. Well, I'm sure most of you know lots of things about self-avoiding walks. But a couple of things that you need from the point of view of this talk are as follows. So we have a self-avoiding walk on some lattice, ZD, which is the d-dimensional hypercubic lattice. But you can think of it as being the square lattice or the simple cubic lattice, if you like. The extension to general D isn't very important from this point of view. Well, let's think of Cn as the number of self-avoiding walks on ZD, so modulo translation, or if you like, you can think of them as starting at the origin on the lattice. So Cn counts the number of these self-avoiding walks. So if I was on the square lattice, C1 would be 4. The walk can go any of north, south, east, or west directions. C2 would be 12. After taking the first step, it can then turn left, turn right, or go straight on. C3 will be 36 by the same argument. C4 will be 100, because now you have to avoid going back and forming a unit square on the lattice. So it's going to be 3 times C3 minus the number of ways in which you can form a unit square, and that turns out to be 100. So you can carry on counting in this way. I don't quite know how far they're being counted, but an awful long way on the square lattice and quite far on the simple cubic lattice. But I'm more interested today in the asymptotics of this. And John Hammersley in 1954 proved that this limit, which is written here, exists. So the limit as n goes to infinity of 1 over n times the logarithm of Cn exists. And it's equal to, in general dimension, in d dimensions, let's call that kappa d. And that's often called the connective constant of the lattice. So that's proved, or Hammersley proved that by using subadditive functions. And I think was probably the first person to use subadditive functions to prove the existence of these thermodynamic limits. And they've been used all over statistical mechanics since then. It was a very, very nice paper with a very beautiful idea in it. The idea dates back to a Hungarian mathematician called Fekete, who initially proved this, and it's often called Fekete's lemma. The other thing we need to know is that kappa d isn't either 0 or infinity, and in fact it's fairly easy to show that it's between log d and log of 2d minus 1. Log 2d minus 1 counts reverse restricted walks, and log d counts walks which only go in the positive coordinate directions. Now, we're going to look at a subset of these, which are called positive walks. So let's suppose that we put on the obvious coordinate system on ZD, which I'll call xy ... z, and the ith vertex of the walk will have coordinates xi, yi ... zi. And a positive walk is a self-avoiding walk on ZD, which starts at the origin and has all z coordinates non-negative. So zi is greater than or equal to 0 for all I. So this means that we have a hyperplane, z equals 0, through the origin, and the walk is confined to lie in or on one side of that hyperplane. Now we're going to count. So suppose that Cn of Vh is the number of positive walks with n edges, with v plus 1 vertices in this hyperplane z equals 0. So that's going to measure the extent to which it's adsorbed. The v plus 1, the plus 1 is there because the 0th vertex is always in the surface. And with Zn, the z coordinate of the last vertex equal to h. I'm going to call that the height of the walk. These v's are counting what are often called visits. So we've got this quantity Cn of Vh, which is a count. And if we form the generating function of that, sum over v and h of Cn of Vh times a to the v, y to the h, that's the partition function for the problem. I'm going to call that C sub n of ay. So if we think of physical variables, A is going to be a Boltzmann factor e to minus epsilon over kt, where epsilon is the energy associated with a vertex in the surface, and y is going to be e to the power f over kt, where f is the force being applied to the last vertex in energy units. Now, there are two special cases. If there's no force, f equals 0, and therefore y equals 1. And if there's no surface interaction, then epsilon equals 0 and a equals 1. So there are two particular cases, and it turns out that those two cases are what really determines the behavior for all a and y. So let's start with no force. So first of all, the limit, lim n goes to infinity, n to minus 1 log Cn of a1 exists. I'm going to call that kappa of a. So that was initially proved. I think that was first proved by John Hammersley, Glenn Torrey, and myself in 1982 or so. It's quite difficult to prove that that limit exists, or at least it seemed pretty difficult at the time. We had to build a battery of techniques to prove the existence of the limit. Anyway, it exists. So kappa of A is a reduced limiting free energy. It's a convex function of log A, which will be a useful property for it to have. And if A is less than or equal to 1, so what does that mean? It means that the surface is repelling the vertices of the walk. So the polymer is being pushed off the surface. And if A is less than or equal to 1, kappa of A is independent of A and is equal to kappa of 1, which is equal to kappa D. Okay, so that means the free energy is a constant for A less than or equal to 1. Now, if A is bigger than 1, then we can get two lower bounds. By monotonicity, it's bigger than kappa of 1, so it's bigger than kappa D. And it's also bigger by a strategy argument than the free energy of a walk, which lies entirely in the surface. If the walk lies entirely in the surface, then its free energy is going to be kappa D minus 1 plus log A. So the connective constant of the D minus 1 dimensional hypercubic lattice. So that's a kind of entropy term, plus log A, which is the energy term that we get from having all of the vertices in the surface. So we've got a free energy which is constant for A less than or equal to 1, and eventually it stops being constant because it's bounded below by the maximum of kappa D and kappa D minus 1 plus log A. So there must be a phase transition. The free energy must be non-analytic. At some point, A equals AC, and 1 is less than AC is less than the exponential of kappa D minus 1. So what I've told you, in fact, proves that, but with the strict inequalities replaced by less than or equal to terms. To turn them from less than or equal to into less than is quite a lot of work, but anyway, it can be done. Moreover, kappa of A is asymptotic to one of the lower bounds. So as you increase the interaction of the vertices with the surface, kappa of A more and more nearly approaches kappa D minus 1 plus log A. Okay, so that's a result we'll need, and the other things we'll basically need on this are the existence of the phase transition, the existence of the original limit, maybe the convex function, and this asymptotic result, which is the last thing I have on this slide. Now, suppose there's no surface interaction. So if there's no surface interaction, then A equals 1. That means F equals 0. I'm sorry, that means that epsilon equals 0. So now we can prove that the limit lim n goes to infinity n to minus 1 log Cn of 1y, call it lambda of y, exists. Lambda of y is a convex function of log y. When the walk is being pushed towards the surface, we can prove that the free energy, lambda of y, is independent of y. So if y is less than or equal to 1, that corresponds to negative f, the walk being pushed, the last vertex being pushed towards the surface. Lambda of y is lambda of 1 is equal to kappa of d. And if if y is greater than 1, then we have a lower bound, again, that by monotonicity, lambda of y is bigger than kappa d. And by a strategy argument, lambda of y is bigger than log y. So the strategy argument corresponds to the walk being entirely pulled into a straight line perpendicular to z equals 0. So there must be a phase transition. And what I've said there gives me bounds on the phase transition, but Yoffe and Velenik and Nick Beaton have proved that the phase transition in fact occurs at yc equals 1, y equals yc equals 1. So that means that as soon as you apply a force, the walk's pulled off the surface and it becomes ballistic. In fact, that is the typical distance of the last vertex from the surface is proportional to the length of the walk. Now, similarly, you can prove that lambda of y is asymptotic to log y, and that will be a useful result as we go along. Now, suppose we have general A and y. So now it turns out that we can prove that the limit lim 1 over n log Cn of ay exists. I'm going to call that psi of ay. And this is a convex function of log a and log y. It's not just convex in log a and convex in log y. It's convex as a surface in both variables. Now, a result which most physicists would regard as being the expected result, turns out that psi of ay is the maximum of kappa of a and lambda of y. It's not that easy to prove. You have to do some work to prove it, but that's what turns out to be the situation. So if kappa of a is bigger than lambda of y, it means that the walk is in an adsorb phase. If lambda of y is bigger than kappa of a, it means that it's in this ballistic phase, at least when a is bigger than ac and y is bigger than 1. So there's a phase boundary, call it y equals yc of a in the AY plane when y is bigger than 1 and when a is bigger than ac, and that's determined by the question of when kappa of a is equal to lambda of y. So if I solve the equation kappa of a equals lambda of y, that determines the phase boundary. I can put in the asymptotics that I have for lambda of y and kappa of a for large A and large Y, and that tells me that the phase boundary is asymptotic to y equals a times e to the power kappa d minus 1 as a becomes very large. And it turns out that you can prove that the phase transition is first order except at AC1 where we don't know what the answer is. So provided that y is greater than 1, a is greater than AC, then the phase transition is first order. I think that was first proved by Tony Gutman, Ivan Jensen, and myself. So what does the phase diagram look like in the force temperature plane? So remember that A is eta minus epsilon over kT, and Y is e to the power f over kT. So first of all, so what I'm going to do is replace A and Y by those quantities and translate the results I've just told you in the AY plane to the force temperature plane. So when D is greater than or equal to 3, it turns out that the limit as t goes to 0 of the derivative d f of t by dt is positive. So that says that at low temperatures, the force required to pull the walk out of the surface increases as the temperature increases, which is at least a mildly surprising result. Because you'd think that as the temperature increases, the walk is more and more likely to come off the surface just for entropic reasons. Well, this is because the walk has some entropy when it's lying in the surface. Think of it think of just the three-dimensional case rather than d greater than or equal to 3. The walk has entropy sitting in the square lattice, and when I pull it off the surface, it loses entropy because it's becoming more and more close to a straight line as it comes out of the surface, a straight line perpendicular to the surface. So lim t goes to 0, df by dt is positive, so the derivative starts being positive, and then eventually, of course, has to become negative as we reach a temperature close to the natural temperature for the desorption to occur, so the phase boundary is reentrant. In 2 dimensions, we don't know if it's reentrant. All we know is that the limit, the t goes to 0 limit of the derivative is 0. So it could start off, well, it certainly starts off with 0 derivative, but then it could rise and then fall, or it could continue falling. However, numerically, we know the answer because Gutman and Jensen did a series analysis study of this, and they measured the force as a function of temperature in 2 dimensions. And you see that the force temperature curve, the phase boundary in the FT plane is monotone decreasing. So one of the things I would like to do, but haven't managed to do, is to prove that that's the case, to prove that the derivative is never positive. So that's an open question. So there are some other homeomorphism types that you might try to look at. So here's a couple of pictures of them. So the one on the left is a star. So a star is a tree where one vertex is degree f, say, and f vertices are degree 1, and all the other vertices are degree 2. So I have a central vertex of degree f, and f branches running out to vertices of degree 1. If all those branches have the same number of vertices of degree 2, then it's called a uniform star. And the picture on the left is a 3-star. So I have one vertex of degree 3, 3 vertices of degree 1. One of those vertices is anchored in the surface. One of those degree 1 vertices is anchored in the surface. And the force is applied at a different degree 1 vertex to pull the star off the surface. So again, all of the vertices of the star can interact with the surface, and the force is applied to pull it off the surface. The other homeomorphism type, the one on the right, is a cone. So now I have a backbone and T teeth coming off this. And so I have T vertices of degree 3 and T plus 1 vertices of degree 1, and it's a tree. And if all of the branches are the same length, it's a uniform cone. So for me, all the stars and cones are going to be uniform. So we can do these 2 problems. So these are 3 stars in Z3, and the free energy you can work out by the same kind of arguments that I was given before. The free energy turns out to be the maximum of these 3 quantities. Kappa of A, which corresponds to the star being entirely absorbed in, or not entirely, but all the branches being partially absorbed in the surface, as though there was no force. Or the second term is 2 lambda of y plus kappa 3 over 3. So that means that 2 of the branches are ballistic, being pulled out of the surface. That's the 2 times lambda of y. And the third branch is flopping around. It's free. It's neither adsorbed nor in a ballistic phase. And the third one has 2 of the branches, 2 kappa of A plus lambda of y over 3. So 2 of the branches are adsorbed, and 1 of the branches is pulled off the surface. So if I just go back, that third case corresponds to the branch at which the force is being applied being pulled off the surface, and the other 2 being sitting in an adsorbed phase. So we have what we call a mixed phase, where part of it is ballistic and part of it is adsorbed, as well as an adsorbed phase and a ballistic phase. Now, there are phase boundaries, of course. Phase boundaries correspond to places where 2 of those free energies are equal. So if the first and third of those are equal, then that means that lambda of y equals kappa of A. So the phase boundary between the mixed and the adsorbed phases corresponds to the solution of the equation lambda of y equals kappa of A. And there's a phase boundary between the mixed and ballistic phases, and that's given by the solution of lambda of y equals 2 kappa of A minus kappa 3. We can do the asymptotics of this. That is, we can do the asymptotics, put in the asymptotic forms for lambda of y and kappa of A. And we find that asymptotically, the boundaries approach those 2 curves, those 2 quantities which I've given at the bottom, y equals e to the kappa 2 times A, and y equals e to the 2 kappa 2 minus kappa 3 times A squared. So we know what the asymptotic behavior of the phase boundaries is in terms of these quantities kappa 2 and kappa 3. So this has been looked at numerically by Chris Bradley and Alex Ovcharek, and they get, they use Monte Carlo methods, they get this phase, this phase diagram in the YA plane. The red curves correspond to their numerical estimates of the phase boundaries, and the dotted lines are our asymptotic results for this. And you see that the red curves very nicely go to the asymptotic forms that we have. And finally, I want to say something a little bit about cones. So you can do the same, play the game, play the same game with cones, and you find that the free energy is given by the maximum of these 3 quantities. So the first is kappa of A, where all of the branches of the cone are sitting in the surface. The second one has this term t plus 1 times lambda of y, which is where the backbone of the cone is all ballistic. There are t plus 1 contributions to the backbone, and each of those is being pulled. And so each of them contributes a lambda of y term. And then t kappa 3 are from the teeth of the cone, which are neither adsorbed nor ballistic. And so they give t times kappa 3, they're all free. And finally, you have a mixed phase in which one branch of the backbone is being pulled ballistically, that's the lambda of y, and everything else is sitting in the surface. So the first phase, kappa of A, is an adsorbed phase. The second one, t plus 1 lambda of y plus t kappa 3, is a ballistic phase. And the last one, where we have a lambda of y term and a kappa of A term, is a mixed phase. And we always have 3 phases independent of the number of teeth. And increase in the number of teeth doesn't increase the number of phases. Okay, so that brings me to the end of what I wanted to talk about. Essentially everything that I've said, except for the 2 numerical results that I displayed, is rigorous. And we have a good understanding at the rigorous level of the phase diagrams for these 3 situations of a linear polymer, a star polymer, and a cone. And we can do a number of other cases, and Bucks van Rensburg, who is giving another talk at this conference, is going to talk about some other cases. Or I should say, in case I didn't say it, that Bux van Rensburg and I were collaborating on essentially everything which I've said in this talk today. Okay, thank you very much for your attention.
Okay, thanks, Sue. Okay, I'll try and turn that sharing off. Stop share. So I guess we kind of have questions, but if anybody wants to make a comment or a question, actually, Stu's here, is he?
Oh, I am here. I just have lousy internet, and so I thought that it was better to pre-record, because if I tried to do it, it would have had all kinds of hot.
So we can have questions. Anybody have a question?
Yes. Yeah, I have a question. Thanks, Stu. Just wondering, so in those, in the combs, you said that the teeth were uniform length. Were they also uniformly spaced along the backbone, or do you allow
everything is uniform?
That to be arbitrary?
No, so everything is uniform.
Okay.
The spacing along the backbone is uniform too.
All right, okay, thanks.
Sorry, Stu.
Yeah.
Yeah. I assume everything's homopolymer, but can be made, or what's the copolymer situation on this?
I think Bux is going to talk about the copolymer situation. We used to mention it. So we have done, okay, so we've done diblock and triblock linear copolymers. And we are in the process of trying to do star copolymers with some difficulties. And I if I'm not mistaken, Bux is going to mention some of these things in the next talk.
Okay, any questions here in Melbourne? Nope. All right. So I think that's almost spot on time. So thanks very much, Stu. Sorry, I didn't realize you were there.